chemistry. He did his postgraduate research at University of Pennsylvania, USA, and continued the research at Joseph Stephen Institute in Slovenia. From there, he moved to UK, where he worked at the London South Bank University and prestigious college, Imperial College London. In 2019, Professor Walland established Material Research Laboratory at University of Nova Gorica, and today the laboratory, with its more than 5 million euro infrastructure and an annual budget of around 1 million euro, employs around 18 researchers of different seniority, expertise, and nationalities. Within the laboratory, he established a group for the theoretical material science, surface science, material chemistry, and the electron microscopy. They have very good electron microscopy facilities, including EM, FESM, cathodoluminescence, and many more. In his career, he was a visiting professor at London South Bank University and Imperial College London. While now he is an adjunct professor at University of Electronic Science and Technology of China. His main research interests are materials and technologies for sustainable energy, catalyst, topological insulators, electrocaloric material, as well as other nanostructure functional materials. He has published more than 200 scientific papers with a citation around 7,000. He is an author of 14 patents. So with this one, I invite Professor Walland to take this lecture, and you are welcome at IIT Jodhpur. Now this one Webex is to you, Professor Walland.
So it's my turn now?
Yes, yes.
So good afternoon in Indian time. In Slovenian time, I would say good morning, but at the same time we are together. So first of all, Dr. Kumar, thank you very much for your kind presentation, and I'm delighted that I can deliver these lectures to your students and help you bringing up their knowledge and their enthusiasm for material science. So I would like to first mention one technical details. At the moment, I'm getting very bad voice quality back, so I would prefer that we communicate on chat. In that way, I will understand your questions better and be able to answer them. So unfortunately, we have to be online. Still, this pandemic is really a nightmare. Otherwise, I would much rather be with you in person and talk to you and interact to you in person. That makes much more efficient interaction and efficient knowledge transfer. So, but we can't do anything about it. So we will do this lecture online, and hopefully it will have the same result. So let's start with kind of the outline of what we're gonna be talking about during this week. Today we will start very slowly, easy to warm up. We'll start with some very basics that we need to understand before we go into more detailed discussion on the functional properties of the materials. So we will talk today about chemical bonds and electronic structures, also about some structural characteristics, especially structural defects. All these things or these features are very important, and in big deal they define the functional properties of materials. So today we will also, sorry, this is my wrong schedule. It is not the one which is relevant now. Today's tutorial will be not on organic networks, but it will be on electron microscopy. And then we will continue with some properties tomorrow, materials properties, mechanical, optical, and thermal. And on the second tutorial will be characterization of materials. Here you have to imagine that it is written characterization of materials. Then we continue with the material properties, about the polar dielectrics, electrical properties. We'll have a tutorial on energy supply and the relevance of the materials in energy supply. And further lectures will be on some combined or coupled properties, like there are electrocalorics properties, for instance. And we will again in the tutorial tackle the sustainability of our life, and I will give you, with the help of my colleague from University of Maribor, really, will give you some insight in hydrogen economy. Then some other things like a thin film and their applications, and magnetic materials and photocatalysis. In between there also be a research seminar, which will be about our real science that we produce in the lab. So if we continue now, here we go. So what I'm going to show you here, well, there are some pastime gadgets. I mean, you are too young to remember them or to know them, but this is just one human lifetime back, you know, when the technology started to boom and we have got first computers, first mobile phones, some first computer games and so on. So in one lifetime, the technology moved from, this is what I'm showing you here, to something like this: flexible electronic, powerful microprocessors, super fast trains, and of course smartphones. And you know, we are traveling to the space. So it's only in one lifetime. However, this came with a price, unfortunately. Pollution of our environment, and this is becoming critical. Global warming, and this is a result of population growth. In 50 years, in 50 years, the population basically doubled, and that is now bringing us a big problem. Now we have to think, and the consequences of this are huge and damaging. You know, weather is getting severe, rainfall is causing problems on one side of the planet. On the other side of the planet, we got drought. And this is critical because a number of the planet population is starving because of this. And these beautiful animals are just about to extinct if we're going to melt down our ice caps. So we really need to think what we want to do in the past. Do we want to develop technology towards more bright, smart gadgets, beautiful technology in hand with environmental protection? Or do we want to go towards some apocalyptic Mad Max scenario of dystopia? So I prefer the first, of course. And the material science has got a big role in that. Namely, when we are developing new products and new gadgets, we have to understand that we have one very important criteria, and this is environmental sustainability of products and the production of the products. So I put it here at the end of the line because of chronological reasons, because this is kind of new criteria, but actually I should put it on the top, because if we don't satisfy this criteria, we can't use new materials and new devices anymore. So I listed a number of criteria. They're all important for a sustainable material. I listed here as a first functionality. Of course, if we want to develop a material for some particular purpose, we need to think, you know, whether its function is appropriate for this purpose. And then its compatibility. Of course, it must be compatible with the use and the other materials in the surrounding. and it must be reliable and durable. So it must reliably work for a long time. This is also environmental aspect. If we need to change the smartphone every 2 years, then we are polluting and loading our environment with a lot of waste and emissions. Shaping capability is important for a material. Normally, we have to deliver a material or a device in some particular shape. So we have to understand how to shape the material, and the material must have this capability. And there's another problem which I can demonstrate on the example of new lithium-ion batteries. The materials must be available, bending. Must be available, because if they are not available, they are basically, we're gonna run out of raw materials and won't be able to produce this material economically at a reasonable price. Now, we're coming to environmental sustainability. So that requires a production of non-hazardous materials, the production that will not emit any toxic emissions or excess of carbon dioxide, and also the products that can be recycled, the products that can be introduced into the circular economy, for instance. All these things we have to understand today, in addition to very technical aspects of the materials. Okay. So materials, as a human beings, they compete for their role in technology. I would like to demonstrate this to you on the case of automotive industry. So this is how the share of different materials has been changing with years. So what we can see is that we're using less metal, but more plastic and rubber, but also more advanced materials like a ceramic, carbon, and composites. However, this trend is not good for environment, because metals are well recyclable, but plastic and rubber, we kind of recycle, but not totally. So we have to think about that, and of course use the plastics which can be recyclable, and of course we have to have also all the lines set up for the recycling. Also, in the terms of the increase in the production, you see the polymers are increasing with much higher rate than the metals. So if we look around us, we see, unfortunately, we see polymers everywhere in our surrounding, and we really need to do something about that. I mean, next to global warming, the plastic in our environment is another very serious threat. You see our oceans are getting so polluted, we have to do something about it. Okay, now let's talk about materials. I think I have put a lot of stress on environmental sustainability of materials, but now we're gonna go into the core of our lectures, which actually is our functional materials, their properties, their performances, and actually what all we have to know in order to develop new functional materials. So what I'm showing you here is a bit of introduction into this, just for you to understand what are all the aspects of material that we need to understand and master in order to be able to process and to develop new functional materials. If this is material science and engineering, and it comprises of understanding material structures and understanding how we process raw materials to produce desired structures, and how these desired structures influence properties. And of course, What properties do we need to get the performance we want? Apart from this, this combination of features, there is also a characterization. We have to have characterization tools, and we have to have knowledge to use these tools to characterize materials in terms of their crystal structure and in terms of their properties and performances. Okay, now we came to the first chapter of our lecture, and this is chemical bond. Our chemical bond defines, in a main way, defines the structure, and the structure defines the properties. So we really have to understand how species, how particles, how ions and atoms are bonded together. As a number of different bonds that differ in their strength and in their character. So we have a group of primary bonds, which are strong bonds. And these are ionic and covalent bonds, as well as the metal bonds. So we will discuss more about this group. And then we have a group of weaker bonds. We call them secondary bonds or van der Waals bonds. And they are bonds between mainly electrostatic bonds. Actually, they are electrostatic bonds. And they are bonds between ions and dipoles in different ways. I mean, they can be permanent ion and permanent dipoles, or permanent dipoles and permanent dipoles, and so on. At the end of the line, there are very, very weak bonds, which we call dispersive forces, which are between induced dipoles and induced dipoles on the other side. So let's look a bit better into the nature of these bonds. So first of all, I would like to talk about ionic bonds. These are bonds between ions. We have a positive cation and negative anion. In our case, let's consider species that are single charged. Cation is positively charged and anion negatively charged. Between them, normally we have electrostatic Coulomb attraction. But when they come together too close, we also have repulsion between them, because the nucleus of these species started to repulse. And these two forces have different character. Now, the overall potential is a sum of these two forces. Now we have attraction here. This is how we describe it mathematically or physically. So we have two charges of two species. And then we have here, we have also the distance between them. And of course, this is a charge of the electron. And we can, with this equation, calculate the force between these two species. And this term represents the repulsion of the species, where in this case B is one constant, and R is distance, and N is again the constant. So what you see here is this is just linear, well, with the power of 1, while this is on power of n. And if we would represent this in the plot, we would see that attraction is decreasing the energy of the system, which is beneficial for the system. We know that lower the system energy is, more stable is the system, while the repulsion is actually increasing the energy in the system. It is almost zero when R is high, it's long, when the distance between ions is big, but it's going very, very highly up when we are coming very close with the species. So the bottom line here is the sum of these two forces and well, energy contributions. And you see this curve has got a minimum here. This is the situation where the energy of the system is the lowest. So it means that the system is the most stable when the distance between them is equal to R0 as it's shown here. So actually this represents the bond between these two species. So these two species in one material system will be situated on the distance which corresponds to R0. We also have to pay attention to the shape of this potential well, as we call it, because this shape can be very different, and the shape and basically the shape, we can say the shape and the position of R0 determines many functional properties. I will show you a few examples. We will discuss that later in much more details. Now, one property is a melting point. So the gases where this well is very shallow or low, they have very low melting points. So this means that the gases are not strongly connected, and the thermal energy can easily break the bonds of solids and make it liquid or even gases. When this well is very deep, it means that the system in its solid form is very stable, and we need a lot of thermal energy to move it from solid to liquid and then later to the gas. Also, shallow potential make the material very elastic, and with a high temperature expansion coefficient, while steep and deep potential makes the material rigid. I'm not going to go in discussion now why this is so, because we're going to hear about that later during the discussion on mechanical properties in details. Now we are coming to a covalent bond. So as you have seen in the ionic bond, there are no sharing of the electrons, but there were like more electrostatic attraction. While in the case of the covalent bond, the situation is different. Here, one ion or atom donates the electron into the orbital that actually goes between both two ions of the same kind or different kind. So we actually get new orbitals, not only atomic orbitals, but also new orbitals, which we call molecular orbitals. So we find this bond in polymers and in diamond, in silicon, germanium, and so on. Silicon carbide is also very covalent material. And these bonds are stronger. Normally, they're stronger than ionic bonds. And we can see this from the melting point of diamond, which is very high, compared to the melting of sodium chloride, which is very ionic material, and its melting point is much lower. I would like to emphasize here that the materials are not fully covalent or fully ionic, but they have predominant character of one or another type of the bond. So we say that they are partially ionic, partially covalent, or predominantly, but not fully covalent. So let's look a little bit closer to this covalent bond. How it's formed, how these molecular orbitals are formed. So here we have two oxygen atoms with their atomic orbitals, energy levels, 1s, 2s, 2p as we know them. And they are, of course, some are fully occupied, and these upper are partially occupied. This is the same situation, of course, for both oxygen atoms. But then we start to bring them together, and what happens? At some point, they merge into the oxygen molecule, and the electron levels completely change. You see 1s level change its energy levels, and instead of atomic 1s level, we have got two molecular levels. From 2 atomic levels, we get 2 molecular orbitals here. You see, one is with lower energy, and therefore it stabilizes the system, and one is with higher energy, and therefore it destabilizes the system. The same happened with 2s orbital, and similar also with 2p orbitals. I would like to spend a few more minutes with 2p orbitals. You see, we have 3 2p levels and on both sides, so this altogether 6 atomic levels form 6 molecular orbitals. 3 orbitals are stabilizing, we call them bonding orbitals, and 3 are destabilizing, and we call them anti-bonding orbitals. Now we have to put all these electrons, 8 electrons, onto these orbitals. Of course, we start with the lowest, we fully occupy it, then next, and then next, but then we still have 2 electrons to put onto the anti-bonding orbitals. But still, all together, all this situation together is more energy favorable for oxygen molecule than for 2 separating oxygen atoms. For that reason, the oxygen molecules will spontaneously form and will not back decompose into oxygen atoms. Okay, this is a situation when we have 2 atoms. But what if we would have like 6 atoms that would want to join together? Now here is the situation, but for the sake of simplicity, I will show you what happens with 1s orbital when we merge together 6 let's say metal atoms. So we have now 6 1s orbitals that form 6 molecular orbitals when these metal atoms are joined into one metal cluster. And 3 of them will be bonding and 6 will be anti-bonding. Okay, but if we have, let's say, a metal single crystal, when we have like enormous number of atoms, what will happen then? So it will happen pretty much the same. We will have then this enormous number of the states here in the bonding part of the levels, and we will also have enormous number of anti-bonding orbitals. However, because of the thermodynamic reasons, because we want to stabilize the system, all the electrons will be located in into bonding orbitals. Well, and we are not having any more electrons to put here on the anti-bonding levels. Now, of course, this is much more stable situation than if we would have all the atoms separated and all the atomic orbitals on the level that normally exist in atoms. Okay, so this is now what we call metallic bond. As you see, metallic bond is not much different than covalent bond, but is actually the consequence of a huge number of the atoms of same kind. So we are coming now to secondary van der Waals bonds. So by their nature, these bonds are electrostatic. and they are significantly weaker than primary bonds. So they can be 10 times weaker or even 1,000 times. You will see later what I'm talking about. So they can actually be a form between ion and a dipole, dipole and a dipole, and ion and induced dipole. I didn't put here a case when they are created form between induced dipole and induced dipole. This is the situation, for instance, with the noble gases, because these so-called dispersive forces are temporary and they are present only for a very short time, because nucleus and electronic cloud are, of course, oscillating in the atom. And in a short period of time, even a noble gas is induced dipole. And in these cases, for a very short time, it can create a weak electrostatic bond with the other noble gas atom. So, but let's look better into the case when we have ion and a dipole, or dipole and a dipole. What you can notice here that I didn't put a case when we have ion and ion. Well, but the reason is because when we have ion and ion, then we are talking about the ionic bond between them. So one very known dipole molecule with a dipole is water. You see the molecule for water here. Oxygen is connected to two hydrogens in an angle, as you see here, and that makes one part of the molecule, water molecule, positive and another part negative. So basically, efficiently, we have here a dipole with a gravity of positive charge on this side when hydrogens are, and the gravity of negative charge on the other side. Now imagine that we have in a system present two water molecules. And when they come together close, of course, they will tend to form a bit of electrostatic bond between the negative and positive part of the molecule. So now you see that these two are oriented. They're not random, just that. They're oriented. And they form the most strong secondary bond, which we call hydrogen bond. And the hydrogen bond is a bond between the hydrogen part of the molecule and oxygen part of the molecule in the case of water. But hydrogen bond can be also formed between hydrogen part of any molecule and very electronegative part of any other molecule, which is formed by nitrogen or fluorine or similar ions. So in the case of water, you see we have this orientation. Now, if we would have more water molecules, we would get more hydrogen bonds, but in the same type of orientation. Now, you can imagine now water. I'm talking about water because water is an important part in processing of materials, and therefore I will spend a little bit more words about the structure of a liquid water. Well, yes, liquid water does have a structure. In a water, you won't find a H2O molecule. Basically, they do not exist in the water, although we think they are H2O. But exactly because of the hydrogen bond, the structure of the liquid water exists. It is flexible, but it also has got some short-range order, and this is presented here. I already showed you on the previous slide how the water molecules bond together when they are in the proximity. So in the liquid water, there's a lot of water molecules in proximity, and they bond, as it was shown on the previous slide, to form such tetragons, such pyramids. and then this clustering continues into big cluster. And what we do have in a liquid water are big clusters of water with this short range order in the form of these tetragrams, tetrahedral symmetries. So as you see, every hydrogen bond atom is connected with one oxygen atom covalently and with another oxygen atom with its hydrogen bond. Now, and believe me or not, if that wouldn't be so, there would be no life on Earth. We wouldn't exist and talk about water today. Well, all this what I told you has got some consequences. All this clustering of water actually results in the fact that at 4 degrees centigrade, the density of the liquid water is higher than the density of ice. For that reason, the water in the lakes or sea or rivers starts to freeze on the top of the water level, not at the bottom. If the water would freeze from the bottom, there would be no possibility for life to develop in the waters in our past. So the water freezes on the top and somehow thermally insulate the liquid water beneath, which makes the life to survive through the cold winters. That is just as an interesting fact. And there's so many other interesting features of water, mainly related to its ability to connect into the cluster, that I could spend really the whole lecture about that, but unfortunately I cannot. So you see, I wrote here that the hydrogen bond at the room temperature is 10 times stronger than thermal fluctuations. We can understand that because the hydrogen, the water is liquid at the room temperature, and we need to introduce much more thermal energy to make it being gas, vapor at 100 degrees centigrade. But let's now finish with these interesting facts about water and go to other secondary bonds. So we have here ion and dipole. If we have ion and then, sorry, we are talking now about ion and induced dipole because other things are basically covered by the example I showed you before. But if we talk about ion and induced dipole, what really happens when some ion comes close to some species that is not charged? It can really induce the dipole. It can attract the positive part, in this case, let's say nucleus, and repulse the electron cloud. So this previously species without dipole, we now create dipole and will be able to form a bit of interaction with the ionic species. So that is also one kind of the secondary bond. Also, of course, if that happens with the molecule of water, the mechanism is pretty much the same. So as I said, these are very big bonds, not as strong as hydrogen bonds. So now you see, all this has got direct influence on properties. Now we can see very close correlation between the energy of the bond and its melting point or boiling point. It's sometimes they are a little bit different, of course. Like, you know, here we see the case of sodium fluoride, but then we have also to consider something some other features like the crystal state and maybe some hydrogen bonding and so on. But in general, we can easily say that a covalent system would have much higher melting points than the ionic systems. Here is a magnesium oxide with an ionic double bond, really, which then, of course, is anomaly in this correlation. Liquids are close to covalent bonds, and again, in some cases, there are anomalies, like everywhere in the world, there in our being, there are anomalies. And then we have also dispersion forces, which I talk about, and of course, these are very, very low melting point materials. Water with its hydrogen bond, you see, well, it's somewhere in between at 0 degrees centigrade. So that was a general trend. When we talk about materials properties, we will go into more details to better understand all these rough correlations that I was discussing now. So since we are at the end of this first introductory chapter, I would now leave the next chapter for our next hour and would like to see if you have some questions questions for me regarding the topic that we have now discussed in the first hour.
Thank you, Professor Valent, for such a nice introduction and the basics of the functional materials. Now, I would like to request participants, if they have any question, they can type it in the chat box. I'll read it. I'll read them on your behalf. Yes, participants, you can ask your question.
Nipun, you can unmute now. Professor Valent, how is the audio quality?
Sorry, as I said, I had this problem with hearing you. Maybe you can also just write a few words.
Yeah. So yeah, participants, you can type your question if you have any.
So we have one question from Mr. Abdullah. He's asking, what is the difference between functional and smart materials?
Can you write to this one, Professor Valent, this question?
Yes, sir.
In the chat box.
Okay. I can try to answer this a bit philosophical question. Well, functional materials, actually, I'll tell you something. I don't know what are smart materials. That is some word, some description. Somebody just put it out without explaining what exactly is a smart material. Functional material is a material that has got some function in a device. We can have active and passive functions. Mainly the passive functions would be in some kind of structural engineering. We would have, of course, passive functions of a material. Sometimes the functions can be active, like the material in the transistors or diodes. And so on. But what smart material, that's very unclear. Somebody says they're like materials, some materials have capability to self-repair themselves, and they call them smart materials. So I never use the expression smart materials, because this is just a little bit of hype.
Thank you, sir. We have another question in the chat box.
So the question was, which bonds do change when liquid turns into gel state? So as we said in the liquid, now in the liquid we have, if we talk about water, we have hydrogen bond. Of course, we have also covalent bond. But the gel state, actually, the gel itself is a big macromolecule normally. So these are, for instance, some citrates that form, or some alkoxide that start to condensate, and actually they form a covalent bond. But this is then, all gel can be then one macromolecule, which still is covalently bonded, maybe metal organic or organometallic system. Well, this is the question. Normally the solvent does not turn into gel, but some precursor which is dissolved in the solvent reacts, condensates, and form covalent bonds, but is still keeping the system very, very flexible with a lot of nano micro voids inside. Well, the question is how we will distinguish if the material is covalent and ionic material. Well, that is a very good question. As I said, first I would like to say that there's no material which is perfectly ionic or perfectly covalent. Normally we distinguish by observing their properties. As I said, more covalent materials, especially inorganic covalent. I'm not talking so much now about organic materials. Inorganic materials, covalent materials are stronger. They're strongly connected with high melting points, while ionic are not. And they do dissolve in the solvents, some in different way. Ionic materials, they would dissolve into very simple ionic species. Like covalent, they normally would dissolve in a complex ionic species, or even complex neutral species. So we don't have one single test to understand which one is ionic, which one is covalent. But we can use ab initio calculations to get better insight into this. So the next question is, why the ideal gases bond? As I said, the bond between ideal gases is mainly dispersive type. So it's temporary bond. It doesn't exist between two species, two atoms, doesn't exist all the time. It exists for very short time, just for the time that there are fluctuations of electronic cloud, oscillation of electronic cloud makes this atom for a very short time dipolar. And then in this dipole induces dipole on the other atom, and for the short time there's a possibility for them to create a bond. And then in the next moment, this bond will disappear. So this is why these forces are in a statistical way very, very weak. Okay, we have the next question. Does the charged ions remain stable in the environment? Why don't they get neutralized? Actually, that's a nice question. Charged ions actually are neutralized in the environment. Let's consider an ion, chlorine ion in the water. The chlorine ion in the water is actually neutralized by the hydration sphere around them. So the chlorine ion in the water attracts then water species, which actually then they mask with their positive part of the molecule. They mask this negative charge on the chlorine ion, and in that way they get neutralized. We will here later also, when we will talk about the piezoelectrics, how the charge on the surface gets neutralized. Yes, it also gets neutralized by attracting the species, oppositely charged species from environment. And that happens in any case. Of course, no species can be just stable when it's charged by itself. Next question. As shown in tabulated data, natrium fluoride have high bond energy but low melting point. Yes, this is the question. This is the reason. There is a bit quantum mechanical reason, and it is due to the very high electronegativity of fluorine. This makes the bond stronger, this high electronegativity, but it still is ionic bond.
Thank you,
So
sir.
do we have more questions?
No, sir. No, sir. As of now, I guess these were the only one for this lecture.
Yeah, we can discuss, I think, in the next lecture. We have half an hour break and then again we will join. So thank you, Professor Valant, and then again we will join after half an hour.
Okay, see you 10:30. Yes. 10:30 my time.
Thank you.
10:30 in half an hour, and see you back on the second lecture today.
Yes.
Hello, Professor.
Hello?
Yeah, good morning. How is voice now?
It's pretty much the same as before.
Okay, okay.
But it's important that you hear me.
Yes, we can hear you clearly.
Okay. So,
Yeah, we can start this second lecture.
yeah. So
Yeah,
just,
please.
yeah. Okay. Okay, we're gonna start now the second lecture. Welcome back. So first, we heard about how particles, ions, atoms, what forces do they use to bond together. Now we're gonna go a step further and see what kind of structures they really create when they bond together. Now, you see, we like order. We put things in order, in lines. We place them on the surfaces nicely, one after another. And the nature likes that too. So in many cases, nature creates very ordered structures. So you see here two man-made ordered structures. And these two are done by nature. You see, these are eyes of the fly. Nice periodic pattern. And this is what you see here is a transmission electron microscope image, high resolution image of the crystal lattice. And every dot here is actually an atom, which is ordered in a very periodic way in a crystal lattice. Now, all these ordered features, they have, as we call, translation symmetry. So it means that in a certain period, the pattern is reproduced, is repeated. And this is one of the main feature of the crystal lattice. Now we will see what kind of ordering there can exist in a material. We have several types of ordering. Let's first stop at the single crystals. This is very long range order. It's actually really nice and complete ordering where the translation symmetry is on very long range. So you see one line is repeating after another line. So this is what we call translation symmetry. And in single crystals, in a bulk single crystal, this happens in 3 dimensions. While sometimes, on some thin films, we can consider also a 2-dimensional long-range order. Then some systems with a little bit less ordering is a polycrystalline material. In this material, we have domains, which we call grains, that are actually single crystals, and they exhibit long-range order, but they're constrained within the domains, and one grain towards the other grain, they exhibit some mismatch, orientational mismatch between the crystals. This is shown here. We have one grain and we have another grain, and there is some mismatch in between, which we called grain boundary. And then we have a material which even less ordering, and we call this amorphous material, like the glass in the window, or some supercooled metals. They can also be amorphous. But, well, you see, also in amorphous material, there is some kind of ordering. Let's have a look on this schematic system here. It's a morphous system. There's no translational symmetry, because you know the patterns do not repeat, but we have around each black circle we have white circle, and we have 3 white circles, and around each white circle we have 2 black circles. So there is some ordering, and we call that short range order. This is typical silicate glasses, for instance, quartz glasses, or as I said, some liquid metals and similar. So now first, but of course we will basically, you know, talk at the moment, we will basically talk about the situation in some kind of single crystals. Let's first see how the particles of the same kind would pack together. So we have here to define the closed pack structure. This is the structure where the most possible part of the space is filled by this single particles, not single particles, but the particles of the same kind. So if we assume now first one layer of these particles, which here is denoted as an A, you know, this layer can pack as it's shown here. These are circles, full circles. Basically, it's a central ion and surrounded by 6 atoms, surrounded by 6 other atoms. And this is the close packed 2-dimensional structure. But when we bring this into 3 dimensions, of course, we can put on this layer another layer of the atoms. And there's only one way we can put this layer B on the top of the first layer, as it's shown here. And these 2, we also can see these particular sites in these layers. You see, this is what we call tetrahedral vacancy. Is a vacancy between three atoms in the first layer and 1 atom on the top of the next layer. Here is the same tetrahedral vacancy, just that the layers are turned other way around. Then we have here octahedral vacancies, and this is actually the vacancies where we can see through. Now it's the vacancy between 3 layers at the bottom and 3 atoms at the bottom and 3 atoms at the top. And it's kind of see-through vacancy. So we have 2 types of vacancies. Why this is important? It's important because when we put the 3rd layer on the top of these 2, we have 2 different possibilities. We can put it like it's shown here, where we cover the tetrahedral vacancies, or we can put it like it's shown here when we cover octahedral vacancies. So we would have 2 different closed pack structures. One closed pack structure would be called cubic closed pack structure, because the unit cell that we define out of these stacks is a cubic one, and it's represented here. You see, this is actually the same situation. While the other one is hexagonal closed pack structure, because we have to define the hexagonal unit cell, and it's shown like here. Both are closed pack structures, because if we calculate the space filling factor, we will see is the same. So what is the space filling factor? I will give you an example. So in addition to both closed pack structures, we also have another which is commonly found in metals, which is called body-centered cubic structure. Now, and this is here represented. This one has got one atom in the middle of the unit cell and the atoms in the corners of this cell. So it's body-centered because this atom in the center, actually, it's in the center of the body of this unit cell. Opposite to the face-centered systems where the atom is in the center of the faces of the cube. And what we're going to do now is we're going to calculate the space filling factor for this body-centered cubic system. I would emphasize here that all these atoms are of the same kind. So here is a bit of calculation now. From this picture, we can understand that the body diagonal is formed of 4 radius of this atom. One here, 2 over the main central atom, and 1 here. So the body diagonal is equal to 4r. So from that we can calculate the volume of the unit cell represented by the radius. So this would be the volume of the unit cell. And the volume of the atoms within the unit cell, of course, is the following. We have one sphere in the body center, and we have all these pieces of the sphere in the corners. And they sum up to another sphere, because this is 1/8 and 1/8, and we have 8 of them. So, and if we divide these two numbers, we can calculate exact filling factor. So this number means that about 68% of the space within the unit cell is filled by the atom. Of course, if we assume that these atoms are spheric and strictly constrained as shown here. Now, if we calculate that for the face-centered cubic system, which is closed-packed system, we will get, of course, higher number. Well, I can leave you for a homework to calculate this number for yourself, but I tell you, it's not very difficult. Just follow the same principle I showed you before. So, but the message here is that the closed-packed structure has got higher space filling factor, about 74%, than the body-centered cubic cell. And the message is also that we can use very simple methods to calculate these things. Now we move to a little bit more complex crystal structures. As you know, not all crystal structures are composed of atoms of the same kind. So we have oxide, nitrides, carbides, halcogenides, and we also have some metallic compounds of different sorts, like intermetallic compounds. In all these structures, we have these species, ionic or atomic species, that are of either different ionic radius or different charge, and all that has to be kind of considered when these particles are kind of combined into the final structure. So there, in addition to what I have already mentioned, charge and ionic radius, we have also another parameter which kind of is important when the structure is built, and this is electronegativity. This is parameter that tells you how strong the species attract the electron. For instance, we already mentioned fluorine ion or oxygen ion. They are highly electronegative because they attract electrons very strongly, and also electrons of other species nearby. So this species, if this species will be present, the system will be very much ionic, because they want to take the electron towards themselves. They don't want to share it in the molecular orbital. Another is charge. Of course, we have to assure the electroneutrality of the crystal. So if we have one ion which is double charged, we have to have on other sides either double charge ion, cation, let's say species of different charge, or we need two of single charged, and that will kind of determine the stoichiometry of the unit cells. Ionic radius is very important, and it is crucial when we build a structure in determining the coordination number and the cell geometry. I will show you this in the next slides. So let's consider these two species, red and blue, how they can put themselves together. Now we are in the two-dimensional space for the sake of simplicity. So of course the blue will want to kind of encompass the red atom in this way in two dimensions, and we see already that we have one situation when the red atom perfectly fit into the vacancy here. In other situation it is too big for this vacancy, and in other situation it is too small. So in this situation when it's too big, it will allow these blue atoms to kind of oscillate around, and you see this bond is not present anymore. So this system is less stable than this ideal system when all is nicely packed together. In this system, when the red ion is too small, it will have a possibility to rattle around this vacancy, and this will again destabilize the system. So again, we can use simple geometry to calculate what is ideal radius of this ion to fit perfectly into this vacancy. Well, I can leave this really for your homework. It's so simple. And we can easily calculate that this comes to about 0.2. So such an ion will make very stable coordination environment, and we can expect then the system to be present in such particular geometry. Now we go to 3 dimensions, of course. The principles are the same, but geometries are a little bit different. So still, if we have very small ion in coordination with very big ions, we can expect this planar coordination, triangular coordination. Here, these are then the ratio of these two ions. If this ratio is a bit bigger, then we expect a trigonal. Then we expect this pyramidal coordination of 4 bigger ions around one small ion, and so on and so forth. So we can even have coordination 8 when the species are pretty much of the same size. There's another very useful tool. Now, we can, if we understand all the parameters of the unit cell, if we know the parameters of the unit cell, and of course the geometry of the system, we can calculate theoretical density. Of course, its density is from the mass of atoms in the unit cell, and well, that is a mistake, and the volume of the unit cell. So how we do that? Very simple, from the known cell parameters. Here is the example of barium titanate and the perovskite structure. So from the known parameters, this is a cubic structure. We can easily calculate the volume of the unit cell. And then what we have to do is we have to also to calculate the mass of the atoms in the unit cell. So in this unit cell, we have 1 titanium green atom. Then we have 6 oxygen atoms. But be careful, each of these oxygen atoms is only with its half volume within the cell, and it's shared with another cell. So we have to take only half of every of these oxygen atoms. So altogether, it comes to 3 oxygen atoms. And similar with the barium atoms, we have them 8, and of course, with only 1/8 of the volume inside the unit cell. So altogether, we have 1 barium atom. Now we use mass of the atoms that we can find in periodic table and calculate the mass of all these atoms inside the unit cell. And when we divide these two numbers together, we would get theoretical density. Now, this theoretical density is useful when we, for instance, produce barium titanate ceramics. We can measure the density of ceramics, compare it to the theoretically calculated density, and then we would understand how dense this ceramic is. Is that perfectly dense without any pores inside, or does it contain some pore inside? There's another very useful tool. When we are this was used in old time mainly, but when they were trying to determine the exact crystal structure and stoichiometry for material, they grew a single crystal and they compared it with theoretically calculated density. And if the numbers were very close together, then they were sure the structure is correctly determined. Otherwise, well, that was indication for some error in the structural determination. I'll also show you that there is like a high ecosystem, high variety of different structural types. Already, like when we're talking about carbon, we have very, very different structures of carbon. Now, this one is a graphite, for instance, when we have layers and connected with van der Waals bonds. Then we have hexagonal diamond, which is the hardest material ever known today. And it's not just regular diamond, it is a diamond which is produced under very, very high pressures only during the impact of meteorites on the Earth. And then we have regular diamond that we can find in here more frequently in diamond mines, and this is cubic diamond. I see all these different structure, but all the particles here are carbon atoms. Then, for instance, we have rutile type structure. Rutile is titanium dioxide. Then calcium chloride structure, lead oxide structure, fluoride structure, and this is perovskite structure, and many, many others. There's this group which I would like particularly to mention, and because it's very complex and very commonly found, of course, all the minerals based on the silicon, so-called silicates. The silicon 4-charged, 4+ ion is always tetrahedrally coordinated with oxygens because of this particular ratio between the ionic radius. And for that reason, this tetrahedron is the basic structural element of the silicates. But these tetrahedrons can connect on a variety of different ways. And depending on this, they form different families of the silicates. So they can connect over corners or over edges. So now as you see, this sign is a symbol of this tetrahedron, and there is a group of silicates that connect over corners, and they exist in this disilicate form, Two very known representatives are olivine and forsterite. They can connect in the form of chain, as it's shown here, so-called pyroxenes, or in a double chain, amphiboles. They can even be layered silicates, like here, and the very known representatives are clays, and the most pure form of clay is called kaolin. Then it's talc, muscovite, we all know this. And they are in the layered form, but three-dimensional silicates are also possible, like feldspars and different polymers of silica, like quartz, tridymite, and cristobalite. Now, a few words about the clays, because we use them a lot. Actually, they are not pure silicates. They do contain some other ions which have to be there actually to compensate the charge of this silicon layer, silicate layer, really. So you see these are like positive, but also some negatively charged ions. So these bonds here is a hydrogen bond. Still, it's strong, but it's not as strong as the bonds within the layer, which are highly covalent. Some ionic, it's a mixture of covalent and ionic bonds, but they're very strong still. For this reason, all these kaolin clays, they have high plasticity, and we can easier break these bonds and get kind of plasticity which make them so apt to be molded and formed into different shapes. Now, another group of material which exhibits high variety in their structural features is carbon. So we have so many different forms of carbon. We can start with the soot, which is basically amorphous carbon, and it's used as a pigment for vulcanization, but also printing. Actually, laser printing, what you print black color is mainly carbon. Then we have a graphite. We know it, graphite in our pencils, but it's also very often used as a moderator in nuclear technology because it absorbs the neutrons. It's also used as an electrode in electrolysis, electrographite called, in a sealing as a thermal isolator. Then we all know diamond. It's very abrasive, hard. It's used for cutting tools and also for spintronic materials where actually the current, the signal, the information is transmitted also by a spin, not only by a charge. And the new forms that have been later discovered, one of the earliest was fullerene, which is good lubricant. So this is a fullerene here, you see, and it can also kind of order this fullerene buckyballs can order into the crystal. Then we have graphene, which is very simple, just a single layer of graphite, but it's still stable, and we can exfoliate graphite into the layers, the flakes of graphene, and it's used because of very good unusual electron transport properties. It's used in electronics mainly. Then we have carbon nanotubes, all kinds of carbon nanotubes which are very strong in this direction here, and they can use them in structural and reinforcement materials and some clinical applications, also for delivery of medicine into the targeted areas. And of course, there is some ambition to produce some kind of carbon nanomachines, where they would be used for targeted tasks, for instance, for degradation of plastic and so on, but there were high hopes, not much results so far. Okay, now we talked about pretty much ordered systems, but you see, nothing is ideal in the world. I like these two quotes. People are like crystals. It is the defects in them that make them interesting. And another one, perfection has one grave defect. It is apt to be dull. Now, this is exactly what we want to focus. Now, we want to focus on the defects, because the defects in the material, the defects give them a special new properties. Well, these properties can be positive or negative. It can be technologically very useful, but it also can be damaging. And we will now go through these structural defects and try to understand their influence on properties. So we can group them into two groups. Point defects. These are vacancies and interstitial atoms. They can be intrinsic, which means they do not involve other kind of atoms, but just parent atoms in one particular crystal lattice. Or they can be extrinsic, and they can be present due to the presence of some other atoms, third atoms, impurities. Then another group are multidimensional defects, line defects like dislocations and planar defects. Grain boundaries, we talked about them, they can be treated as the defects, staking faults, slip planes, and so on. So here we go now. First, point defects, intrinsic point defects. So I said vacancies. That simply means that one particular particle is missing in the lattice. So other particles, they accommodate to this defect, and of course they move a little bit towards the vacant site, which means that there's a strain generated within the lattice. So all these intrinsic point defects, they are associated also with the strain field in the lattice. So there's a special notation we use to describe such kind of defects. So if there is a vacancy, a symbol for the vacancy on the particular atomic site is like that. So V and in a subscript M. Now, there's one thing. Don't ever promise to give your girlfriend or boyfriend a perfect crystal, perfect diamonds, because it does not exist. It is thermodynamic necessity that all the crystals have got some defects. So it's impossible to grow or to find an ideal, perfect diamond. And we will talk later. I will explain this to you, why this is so. But first, let's just spend a few minutes with this notation. It's called Krogel-Fink notation. Now, the situation becomes a little bit more complex when this atom or ion, which is removed, is not neutral, like in metals, but is charged, because we cannot remove charged atom without compensating this charge. So if we remove positively charged anion, we have also to remove cation, or we have to find somewhere some electron which would compensate this. So we always need to think about compensating the charge. Now let's see what can happen if there is a cation removed. So we produce the vacancy on the M site, yeah? So this, the anion, if the anion stays there, so nothing happens with them, and this is the removed cation. Now we need to have this extra electron somewhere. In this case, we have it localized on the vacancy. So there is the electron on the vacancy there. But the electron can also be delocalized, so can be anywhere on the lattice, just traveling around. So we can have then these two particular situations. Now, if anion is removed, it's the same. We are talking about electron hole localized on the vacant site, or electron hole which is highly mobile and it's delocalized over the crystal lattice. But it should be there to satisfy the charge conservation rule. Next point defect is interstitial atom. Now this is one extra atom which is squeezed into the lattice. So this normally this extra atom occupies some vacancies, but like a intrinsic vacancies that are in between, or maybe we can rather call them the empty space between the original atoms. And of course, if the atom wants to squeeze in, it has to push away the neighboring atoms, and again there would be strain field associated with such kind of the defect. We can, in the Krogel-Fink notation, we can write this like that. It's an atom on the interstitial site. Now these large strain fields are not very favorable for the system, for the crystal system. It highly increases the energy of this system. So the crystals invented a mechanism to reduce this strain field. And this is done by combining different defects in one structure. So one possible combination is, when we talk about vacancies, that in addition to removing anion, we also remove cation. We would have two vacancies, but the strain field would be significantly reduced. And this is quite often the case in ionic crystals. And we call this kind of situation a Schottky pair. I apologize, there should be Y at the end of this Schottky. Schottky pair, we call this Schottky pair. Schottky pairs in ionic crystals are very common. There's another pair called Frankel pair. And well, that happens when some particular ion changes his position from a regular site, which is led by a vacancy, into the interstitial site. So we have a vacancy and the interstitial atom. And this again reduces the strain field. Okay, now I will explain you why you can't have an ideal perfect crystal. It's very thermodynamically defined feature of the crystals. So we know how we write down the free energy of the system. Delta G is delta H minus temperature delta S. Well, we have this enthalpy and entropy term here. So if we produce a defect in the crystal, that absolutely increases the enthalpy of the system, destabilizes it. And this is shown here. You see, the higher defect concentration, higher is the enthalpy of the system. This term destabilizes the crystal. However, we have also entropic term here. So more defects, more disorder in the system, of course, and that means the entropy increases. And the increase in entropy is beneficial for the stability of the system. So because we have this minus sign here. So, and if we take this now, this free energy with both terms, we can easily see that at some point, especially at the beginning, because delta S is decreasing, actually with minus sign here, is decreasing much faster than enthalpy is increasing. So we have initially the stabilization of the crystal coming to some equilibrium defect concentration where the system is the most stable. And then we are, with a further increase in the defect concentration, we are destabilizing the system. So the consequence of this is that at any temperature higher than 0 K, the crystal has got some equilibrium concentration of the defects. And that this equilibrium concentration of defects depends on the temperature, because this curve depends on the temperature. We have temperature here in this expression. Now let's see how this concentration is, defect concentration depends on the temperature. We can describe it with so-called Boltzmann distribution law, which is often met in the nature. Density of atmosphere is changing with such distribution law. The electronic excitations are changing. But we will now talk about the defect concentration, how it is changing with temperature. We said it is changing. And if we write this curve here, we would get this particular one, this particular curve here. So 1 means that we have present only defects. That means, our crystal will disappear. 0, it is perfect crystal, no defects. So now the question is, where on this curve are we when we are at the room temperature? Are we very high up or are we very down? So let me show this on the example of some metal. Now, the formation energy for a vacancy in a metal is around 1 electron volt. So this is this particular term here. So then we can easily calculate that the temperature of about room temperature, we have a 10 to minus 18 defects, the share of defects in the crystal. That is still very, very low, 10 to minus 18. And actually, we can't detect really this small number. Now, but if we heat up, let's say, an iron slab, then we will increase the share of the defects to 10 to minus 5. And that is already high, and it's already measurable. Now imagine that we then immediately cool down such a slab to room temperature. If we don't allow that a new equilibrium would take place, then we would end up at the room temperature due to kinetic hindrance. We would still have all this high number of the defects, and such a material would have significantly worse mechanical properties due to all this high concentration of defects. Now I would like to spend a few minutes with the extrinsic defects. These are impurities, mainly impurities, or more deliberately included dopants. So as no material can be 100% without intrinsic defects, it cannot be also without any extrinsic defects. Every material has got some impurities. And let me just tell you as an example, now we would consider this material as very pure, 99.9999% pure. But still, such a material would have 10 to 22, 10 to 23 impurity atoms per square meter of the material, which is significant. As intrinsic point defects, also extrinsic point defects can be interstitial or substitutional. So you see here these examples, and of course, because of different ionic radius of the impurity atoms, again, the strain field is formed around these defects, similar as we have seen before. There's another thing here I would also like to introduce it to you, and these are solid solutions. Now, when we are talking about small concentration of dopants or impurities within the crystal lattice, it's very likely that this small concentration will not change the symmetry of the crystal lattice. And if this happens, we call that we are within the solid solution range. So the solid solution range exists in the concentration range of the dopant until the symmetry of the crystal lattice changes. When it changes, we produce a new phase, a secondary phase. And we call this critical concentration, we call the solid solution limit. Now, how extent of this solid solubility limit, it's proper solid solubility limit, the extension of solid solubility limit depends on the nature of the dopant, of its size and charge. If the size is very different than the size of the parent ions or atoms, the solid solubility limit will be low. If they are more similar, the solid solubility can be very high. In some cases, it can be the complete solid solubility from one end to another end. We will have the same crystal symmetry. I think this is the case often between metals. You know, that if we mix metals in any concentration, they will maintain the crystal symmetry. But of course, not all, just some very similar metals. So here you see how this is happening. You know, we are adding more and more dopants into the crystal lattice, and still we are not changing the symmetry. But when we exceed this solid solubility limit, somewhere within the system, we will start forming the new secondary phase with a different stoichiometry and different crystal structures. So the solid solution range has got some features which we have to understand. The crystal structure of the parent phase is conserved, despite we are pushing in new type of the atoms. So we need to see no change in the space group. Of course, we should not detect secondary phase, like is the case here. And finally, the composition of the solid solution is homogeneous. So it means that the dopants in the solid solution should be randomly distributed, not grouped or clustered in one part of the system and depleted in another part. So as a consequence of all this, what we see really efficiently, we see in XRD pattern, for instance, we see that the unit cell volume is changed. And in majority of cases, the unit cell volume changes linearly with concentration of the dopant, as what we call Vegar's law. So after this linear relationship changes, we know that we have overcome the solid solubility limit. Okay, just few final minutes to show you line defects, multidimensional defects. One very often seen is dislocation. So we see this location here, and dislocation really is an extra plane of atoms squeezed into the lattice. So this one here, and this is dislocation, and we can see dislocation sometimes already with the optical microscope, because again it creates a significant strain field around the dislocation. So this is what we actually see here. We don't see the dislocation itself, but we see the strain field. Now, and this has got very strong influence on mechanical properties. Let me tell you, we will discuss this later in details when we're going to talk about mechanical properties, so we can leave it like that now. Another is a screw dislocation. We don't talk about any extra plane here, but we just talk about the shift of the planes, like it's shown here. And then when the crystal grows, it grows around this dislocation, around this dislocation. It is shown here in such a spiral way. So silicon carbide is a typical representative with a lot of screw dislocations. Now we got stacking faults, and in metals, a lot of that is present. And the reason is we already know that the planes can stack in two different sequences. In the cubic closed pack and hexagonal closed pack system. But in some cases, you know, the third layer can partially stack in the cubic way, and other part of the third layer can stack in hexagonal way. So, and in between of these domains, we would have stacking fault. Then can be twinning. So twinning is typical for, let's say, ferroelectrics or ferroelastic materials, when actually we don't change any symmetry, but just we kind of mirror the one crystal domain towards another crystal domain, and is shown here. So we have twin plane in between, and the mirror image of one crystal against the other crystal. So please remember this, because we're going to talk later also about the ferroelectric domains, where typically we meet such a situation. And now I think I came to the end of this lecture. And the reason I'm showing you this beautiful snowflake is not that the Olympics has finished yesterday, but because the snowflakes wouldn't exist if there wouldn't be structural defects in ice. The snowflakes are a result of the structural defects in ice. So what you see here in one branch of the snowflake is dislocation line. And this is the tip of dislocation, and the ice grows along dislocation very fast, but normal to dislocation very slow. For that reason, we get these branches of the snowflake. And you see here another dislocation happened, and it grew into yet another direction. So all that makes, as I said before, the defects makes us interesting, and the defects makes the nature interesting. So thank you, and now I'm waiting for your questions.
Thank you, Professor Valent, for this excellent lecture. So, Nipun, can you take the questions from chat box, or you can type in the chat box?
Okay, I got the question. What's aim to use graphite in thermal isolators? Is that it used as a graphite rods or graphite powder? Actually, the graphite used as a thermal isolator is where there is for the high temperature isolation. And normally we can produce graphite also in the plates. So they can be mainly they can be plates.
Thank you, sir. Yes, participants, if you have any other question, you can type it in the chat box.
Okay, so if there is no further question, I think we are at the end of today's lectures. Is that right?
Yes, I think one more question.
Are these defects permanent? Well, no. Defects are not permanent. They can change, they can diffuse, they can annihilate. If you would have like opposite defects, they can annihilate. We can introduce them, but we can also relax them with, let's say, temperature. We will talk much about that later, especially when we're going to talk about the electric properties and mechanical properties. Okay.
Yes, sir. So we don't have any other question, I guess. So may I request Professor Mahesh sir to please take on from here.
Okay, if we don't have any question, then yeah, thank you, Professor Valent. And then we have the tutorial. So today, basically tutorial is on the electron microscopy, how this microscopy is working, and we'll give the demonstration this on the microscopy. So thank you. I think with this one, we will close this session.
Okay. See you later in the tutorial.
Thank you, sir.
Yeah, thank you.
Okay. Bye-bye.